Hello, Mr. Jones here. We're now doing AP Chemistry Notes, pages 62 through 64, although there really isn't anything on 64 of new information. Starting here with what's called the common ion effect. Up to this point, when we've done a problem like calculate the solubility of some compound, we've pretty much always done it in pure water. Nothing else was already in the water. Well, now what we're looking at is what if something else is already dissolved in the water? Specifically, what if it's a common ion? A common ion means one of the exact same ions that we're trying to dissolve. So in this case here with calcium carbonate, well, when calcium carbonate dissolves, you don't get that. Oh boy. You hopefully, if this works right, you get calcium, that's better, and carbonate. Ions like that. And in this case, what's already in the solution is this concentration of sodium carbonate, which would have sodium ions and carbonate ions. So in this case, the common ion is the carbonate, because we have carbonate that we're trying to dissolve, but there's already carbonate in there. Now you might say, well, won't the sodium also cause a problem? Because that's what's going to happen here, is it's going to be harder to dissolve something because there's already ions in the solution. And the sodium will cause an issue, but it's more complicated to calculate. So we're just going to focus on the common ion that is here. And like it says, things are less soluble if there is a common ion. So to the first problem. Estimate or calculate the solubility of calcium carbonate in this solution. So you do it the same as if it was in pure water. You just have to factor in the concentration of the carbonate. So write out a typical equilibrium situation like I have. Let's go back to a more traditional pen here, like I have here. Solid on the left, dissolved ions on the right. Do an ice chart. We're solving for this right here, called the molar solubility, unless it tells you to do something different. We get an X like usual, and we get an X here like usual. Now what's different is normally in pure water, this is 0, and this here is 0. Now, let me not cover up that point. But this time, it's in 0.1 molar sodium carbonate. So when that dissolves, it's going to give off 0.1 molar carbonate. So that's where this 0.100 comes from. So you factor that into your calculation, and you end up getting an X here, X plus 0.1 here. Plug that in your KSP expression. So KSP, here's X for the calcium, and here's the X plus 0.1. Now you can go ahead and solve the math here, but we can take a shortcut. And you might remember last year when you did Ka and Kb calculations for weak acids and weak bases, when there was an X added to something, like what we have here, X plus 0.100, when you have something like that, what you can do is you can assume X is small and remove it. What we're saying is X is going to be so small, adding it to 0.1 will not be significant. Now 0.1 is not a huge number, but X is going to turn out to be way smaller. In this particular case, you'll see here, X ends up being 10 to the negative 8. It's so small, we don't even need to worry about it. So what you do is you get rid of this X here. Don't get rid of the other X. That X is important because that represents the calcium ion, and that is the only calcium ion that exists. This 0.1 represents the carbonate that was already in solution. So when you do that, you get an easier situation. I plugged in the KSP. We still have X here. This becomes just 0.1. And now the math is a lot easier. You end up getting 5.0 times 10 to the negative 8 molarity, because this represents molar solubility. It's the moles of calcium carbonate that will dissolve per liter. So it should have a unit here. Now, if you do the same calculation, but you do it in pure water, you will get a molar solubility of 7.1 times 10 to the negative 5. So you'll see this was a significant difference. If it had been water without the sodium carbonate already dissolved into it, we get 10 to the negative 5 molarity dissolved, whereas because of this stuff being in there at the concentration it's in, it's 10 to the negative 8. So you might be thinking, this assume X is small thing. Are we okay to do that every time? And the answer is yes. There are scenarios where you shouldn't assume X is small, but we are not going to deal with that right now. We will save that for later. So I have a note here. X will always be small enough to assume and take it out like we did here. Next problem is similar, but it does throw a couple of things to be aware of. This time we're trying to dissolve magnesium hydroxide. So I write out my equilibrium system, again with the solid on the left, dissolved ions on the right. Ice chart, we're solving for this. And this time, we're going to put it in a 0.05 molar solution of barium hydroxide. So the common ion in this case is hydroxide. Notice barium hydroxide, which is already dissolved. When this dissolves in water, you get barium ions, you get 2 hydroxides. That's important because if we say that this is 0.05 molarity, that means once this dissolves, the barium is 0.05 molarity, which we're not concerned with. But the hydroxide is double that, it's 0.100 molarity. And that right there from the already dissolved barium hydroxide is where that came from. That is the hydroxide already in solution before we attempt to dissolve magnesium hydroxide. Now, magnesium hydroxide also gives off 2 hydroxides right here. That is not where that 0.1 came from. The 0.1, I need to really emphasize this, that 0.1 right there, that one, it came from the barium hydroxide. Now, when you do your X for your ice chart and your magnesium hydroxide, again, we have our X here, and we have a 2X here. That 2X, that came from the equation that's in the ice chart. That came from the magnesium hydroxide. So it's a coincidence that they both give off 2 hydroxides, and it's important for you to understand that the 0.1 came from the barium hydroxide and the plus 2X came from the magnesium hydroxide. You continue with the problem, you get an X down here, a 2X plus 0.1. plug it into the KSP expression. So KSP is x, and 2x plus 0.1 squared. Again, assume x is small, so we get to get rid of this right here. And if x is small, double x is still going to be small enough we don't have to worry about it, so that's gone. That simplifies the math. So here's the KSP, here's the remaining x, here's the 0.1. Keep the square root, of course, and you end up getting an answer of 6.0 times 10 to the negative 10 molarity. Again, if you do the calculation in pure water, you get a much higher value. You get 10 to the negative 4 molarity, which shows, in this case, it really affected it. It made it so that we're not going to get very much magnesium hydroxide dissolved at all. Okay, next. Dissolving precipitates. So at first, this shouldn't make any sense. The whole idea is that a precipitate is not dissolved. So when you read this, you should kind of say, what the heck are we talking about? Dissolving precipitates. If it's dissolved, it's not a precipitate. Well, what I'm saying here is we're going to take a precipitate and we're going to modify it so that we can dissolve it. So we aren't actually dissolving the precipitate as is. What we are doing, and this might even be a better way to name this, would be modifying precipitates. So they will dissolve. Now that's a long statement. So that's why I just chose to call this dissolving precipitates, but this is a better, more accurate title. Anyway, there are two common methods that we're going to look at. Number one here, number two here. The first method is you can add strong acids to modify what are known as basic anions. Now, we haven't gone through the list of what ions are basic when you put them in water and what anions are acidic when you put them in water and what anions are neutral. We'll be doing that next unit. What this means is certain ions, when they're in water, ignoring all other ions, will make it slightly basic. And an example of that is carbonate. Carbonate by itself in water will make water slightly basic. So take this precipitate, calcium carbonate. And let's say we have this precipitate and we want to get this dissolved. What we can do is add a strong acid. And the only thing that is important here is H+. The acid, the H+, will attach to the carbonate, changing it from carbonate to something else. In this case, it happens to turn it into hydrogen carbonate. Actually, that wouldn't be the right name for that. That would be carbonic acid would be the proper name for that. Hydrogen carbonate would be this. And there is going to be a little bit of that present as well, but for simplicity, we're not even going to focus on that. So notice, we're not dissolving carbonate along with calcium, because calcium and carbonate, when they're in water together, they actually prefer to be bonded and precipitate, unless it's an amazingly low concentration. We have modified the carbonate to this new form right here, so that now we don't have calcium and carbonate in solution together. We have calcium and carbonic acid together. Another example, and this one we're really going to look at in detail, is doing what's called a complexing agent. And this, again, it will modify one of the ions. Now, we haven't really talked about what are called complexes yet. And no, I don't want to restart my computer. This would be bad timing. What happens is you can take ions and you can attach things to them. So in this case, we're going to be taking silver ion, and we're going to attach some ammonias. And they are going to form this complex that you see right here. And this is the first time we've talked about this, if I remember correctly. Like so. And what you can think of is the two ammonia molecules are attaching to the silver and thus modifying it and making it so we aren't trying to dissolve silver and chloride ions. That you can't do that very well. What we're doing is we're modifying the silver into this complex ion here again, and we're going to dissolve that in chloride ions. So it's important to notice this modification that we're making. Now, you might notice that in this case, I added 2 ammonias. Don't worry about that too much right now. We'll cover that in more detail later, but that is a very common thing. Whatever the charge of the ion is, when you attach something to it, you double the attachments. So we're attaching ammonia. Since the charge is +1, we attach 2 ammonias. Had the charge of silver been +2, we would have attached 4 ammonias. But that is not the main issue right now. So I mentioned a demo. I'll see if I can find somebody doing a video of this. But in a prior lesson, I typically show everybody a precipitate of of silver chloride. And then what I can do on this day is I can make that same precipitate, and then I'll add a bunch of ammonia, and I usually use really concentrated so it's effective. And what you will see is that the precipitate will dissolve. I can then reverse the process by removing the ammonia or by adding Cl-, and then I can make the precipitate reappear, and I can just keep going back and forth like we would with any typical equilibrium shifting situation. So let's take a look at this particular system of dissolving the AgCl. It says, consider the reaction in which silver chloride dissolves in ammonia and eventually reaches equilibrium. Same thing as before, silver chloride, adding ammonia. The ammonia is modifying the silver ion to form, again, what's called a complex ion. Just think of it this way, it's an ion and it's complex. And Cl-, which is the typical ion that would come from silver chloride. You might notice when I introduced this concept above, in number 2, I did a single arrow. That was just because I was showing what was happening, but eventually it will reach equilibrium, and so that's what we're looking at now. So that's why those arrows are different. Letter A, the KSP of silver chloride is 10 to the -10, which is no surprise. It's saying it doesn't dissolve very much. The Kf of the complex ion of silver and ammonia is 10 to the +7. That is a massive difference. In other words, this is saying this silver ammonia complex ion, it likes to exist. And it also is soluble in water. So this is going to help. Now you'll see that this here says Kf. What that means is it means formation. So Kf, it's equilibrium, and the F is formation. It doesn't mean formation like we did in thermochem. In this case, it's the formation of a complex ion. So it's just the equilibrium of forming the complex ion from its parts, which are silver and ammonia. So A says calculate K for this reaction. In other words, what's the overall equilibrium constant? Because we have two things to consider. We have to consider the solubility of AgCl and the formation of this complex, the Kf. So what I did here in A is I first wrote the appropriate equilibrium equation for AgCl in water. So AgCl solid on the left, double arrow, and then the two ions dissolved. And I put the KSP value with it. KSP is 1.8 times 10 to the negative 10. Again, whenever you do a KSP expression, always put the solid on the left and the dissolved ions on the right. That's how it's done. I now need to write an equation showing the formation of the complex ion. So here's my silver. I already switched colors, good. Here's the ammonia. I did two of them because there's a 2 up here in the original equation, way up here. And then it's going to reach equilibrium with the complex ion, Ag and H3, 2 with an overall charge of +1. By the way, that +1 applies to the entire thing. In this case, it said that the Kf, the formation of the complex ion, is 1.7 times 10 to the 7. If I add these two equations together, and let me tidy up my screen here a little bit, get some of this stuff out of the way. There we go. If you add these together, I always like to put a line between my overall reactants and my overall products. You'll see that the Ag plus cancels. Everything else is unique. So you just bring it down and you end up with AgCl solid, 2 aqueous ammonias, the complex ion, and the Cl minus. Just kind of going along for the ride. There's not a whole lot to say about it. When you add equations like we just did, you don't add their equilibrium constants. You have to multiply them, or as I like to say, you have to mathesize. So if I take both K's, you multiply them. In this case, you get a K of 3.1 times 10 to the negative 3. Now, I've never seen this K given a special term like KSP or KW or KA or KC and KP that we did recently, but I like to give one just for the fun of it. So since I'm combining KSP and KF, sometimes I like to, let me scroll this up. Sometimes I like to call it KSPF, just saying that they're combining these two things. Or I even had a students once, they like to call it KDP for dissolving precipitate. This one on the left is a little more accurate because it's actually referencing what things were combined. You can just call it K if you want, but if you can give it a little more meaning, that is nice. All right, so we have the K for the situation that's happening. Question B says, calculate the molar solubility of AgCl in 6 molar ammonia. So let's see how soluble this is in 6 molar ammonia. So you take the equation that's given, do an ice chart. So same equation here. Ice chart like usual. We're solving for this. It's that same thing that we usually do. It's the change in the solid. We don't care about this here, and we don't care about this here. Now, this looks a little different than a KSP expression because we are doing this complex ion thing, so that's why it looks a little bit weird. The concentration of ammonia is 6. Students at this point might say, wait, what about that 2 right there? What about that 2? They get all excited about that 2. You don't factor that 2 in. This 6 molarity, that's the concentration of the ammonia. The fact that the reaction consumes 2 of them, that hasn't even happened yet. This is before this equation happened. So just take the 6 as it was given to you. These were nothing before. And then just fill out the chart. If this is an X, I'll do blue now. If this is an X right here, this is a negative 2X plus X plus X. Bring everything straight down and then write out your equilibrium expression. So this is the equilibrium expression for this reaction that we have in letter B, products over reactants. Again, you can call it K if you want. You can call it K, SPF, or whatever makes sense. If it was a KSP expression, there would not be anything in the denominator, because there never is. But this is not a KSP expression, so that's okay to have that ammonia down there. Plug in the K that we solved for here in A. Plug in the values from the equilibrium row, so you get X times X here over 6.0 minus 2x squared. Fortunately, we have perfect squares, so take the square root of everybody. You end up with this. Combine like terms, and you end up getting an X of 0.30 molarity. In other words, this way back here, that X, is the saying in 6 molar ammonia, you can get 0.30 moles of silver chloride dissolved per liter. Now, just out of curiosity, I added a question C. Let's compare this to the molar solubility of silver chloride in water, no ammonia. And I didn't go through the work, but this is where you would write out a KSP expression. So you would just say AgCl solid, and you do the normal thing where you have Ag plus aqueous and Cl minus aqueous. Do a nice chart like usual, do a KSP expression, and go on your way. And in this case, you get that. Let's focus on the 10 to the negative 5. That is a lot less stuff dissolved compared to the 0.30. This shows that it works. Now, this is a pretty complicated system, and there was a lot of new things introduced here. So I'd recommend take a moment and practice this complex ion situation, this thing that I have here. So you can just get a little bit more comfortable with it since it's new. And there's a lot happening here. So it wouldn't hurt for you to go and practice letter A a couple times, where you have to write out and add those equations. It's good practice for the last unit of adjusting K values. And then practice letter B so that you can follow what's going on here, since it's a little bit complicated. And then the last page just has a chemistry picture that I found on the internet, so I could put something on the page. There used to be something there in the notes, but we don't do it anymore. And I'll talk about that note in the homework in class. And that should do it.